on thermodynamics. We get to move on. So I have a couple notes. One is demos. So next week at this time, you're all going to be doing your demo. So look up ideas and talk to me sooner than later, because as they get picked, that then starts limiting you. And a comment that just happened, because some people came during office hours, is they said everything was so simple. Last year it was actually, so I can talk to you how to make it more complex. So some of the best ones last year were really simple ones, and then we just added dimensions, like doing it 3 different ways or something. The only thing due today is the QA labs, and so there's going to be 3 of these. So QA1 has a video. It's only 15 minutes or 10 minutes if you watch it 1.5 time. And yeah, have fun with the flow chart. That should help you also with the post lab, as well as the intro has the answers to it. And I do have an office hour later today. A question that came up during office hours also was about one of the post lab, and this keeps coming up with, there's again 3 QA labs. So these labs don't have calculations, they're qualitative, they're visual. But anytime it makes a complex ion, like in the instructions or something, like the step where you add mercury, you add ammonia to the mercury, and the mercury precipitates and the silver suddenly forms a complex ion, that means it's aqueous. Complex ions are extremely soluble, which means they're now in the supernatant. The other discussion I had with somebody is, whenever something's in the supernatant, you don't actually know if it's there or not, because you can't, we don't have those special eyeballs like the gnomes have. So a precipitate you can see because it's a solid that's formed, but the supernatant is kind of like everything's invisible in there. So something you can ponder. And this is also some flow charts. This is not actually your lab. This is my other class had a lab. So this was somebody. This is a flow chart that got a lot of bonus points. So yeah, like Max and me, we would not go here with our flow charts, but I had some people who did some pretty amazing stuff. So for those of you who love your artistic stuff, you saw my flow chart on the blackboard or the whiteboard behind me as I was making it, and making a flame was about as far as I could get. And this was somebody else who was very artistic. This is something I loved because they went up with their flow chart into the tree. And so anyway, if you're artistic and you want to have fun with your flow charts and allow see, her flow chart actually continued and I just printed it incorrectly. So there you go. You can have an octopus. All right. So we're doing thermodynamics. And most students' memory of thermodynamics from Chem 221 is, when we're live, like, yes, they're all muted, but I can see some faces, which is really nice. Thank you for everybody who has their camera on. Is they're like, oh my gosh, we're doing thermodynamics. My goal is, like, by the end of tomorrow, you're like, what was the big deal? It's thermodynamics. This was cool. So we're doing thermodynamics, and then for the next 2 days, and then our last thing is oxidation reduction. So we're going to be bringing back a lot of stuff from 221, but thermodynamics is a lot more than just enthalpy. In 221, we looked at an intro to it, which was the study of enthalpy. So here we go. What is enthalpy?
The change in heat.
It is the change in heat. For us in chemistry, we're going to have a chemical reaction. So everything's going to be about writing chemical reactions. So in one word, enthalpy, and that's what the H is for, is heat. You can't actually know the amount of heat. So I don't know who said that.
Damon.
Damon, oh. Oh, that's because you haven't spoken up in so long. I didn't recognize your voice. That's really funny. He actually said it brilliantly because he said change. So we can only know the change in heat. So I can know that if I go outside, like today, it's cooler, or if I put my hand on the desk, oh, my desk is pretty warm today, so it's warmer than my hand. So that's what that triangle is change. So it's a measurement of heat change, in our case, in a chemical reaction. So the delta, you'll hear me say delta H. So delta that's a Greek symbol for a capital delta. And so that's what enthalpy is. And the first law of thermodynamics, anybody know? First law of thermodynamics? I love this because they call them laws, but you can't create nor destroy energy. So energy cannot be created nor destroyed. It changes form. So, and so that's the idea of how we get electricity is, so conservation of energy. That would have been a more elegant way of saying it. Is we have the water movement over the dam creates a magnetic moment right in the copper coils, and we create electricity that lights up our house, lights up our life, whatever. A lot of you are going to be taking physics. When you do this in physics, it is the first law deals with energy, and energy would be change in energy. And so Q is heat, and W is work. Oh, it tells you that right there. And so in physics, you work with both heat and work. In chemistry, we pretty much just deal with heat. And so just be aware of that. They have all these wonderful formulas you get to use. All right, this you should all know. Exothermic and endothermic, we've been doing that like for the past 3 weeks because that's how long we've been together. All right. So exo means to exit. So heat, therm is heat, so heat exiting. And in terms of a chemical reaction, that would be as a product. So you're losing heat. So we've been dealing with this with Le Chatelier's principle and equilibrium. And if you want a spoiler alert, it's why we get to come back to it. Oh, we're going to get an equation that puts all of this together. Just wait till the end of the week. We get to put the whole term together in one question. And then endothermic, of course, means heat is going into, or it's a reactant. And so, if nothing else, this is I have graded your exams. I would like to post them as soon as possible. And so pretty much everyone did at least as well or better, and some people did quite a bit better, which was really nice to see. Yeah. The thing I was going to say, you're probably never again in your life going to have to go through all those calculations for titration. So many of you like ace that page, but you all know pH now. You have you're never going to be afraid of the idea of pH and the concept of pH and acid and bases, hopefully. And the same with exo and endo through this term, because we're going to use it a lot now, but those concepts should be pretty well ingrained in you. All right, the new piece that we're going to talk about is entropy. So, anybody, in one word, big challenge for some of you. In one word, what is entropy?
Chaos?
Chaos. There's a better word. Chaos is gases, and gases are about entropy, and we're going to get there. That's our states of matter, is about gases. Does anybody know what the better word is than chaos? Or the word that they usually use, that's always used. Entropy is about, the word that is used is disorder. Which, I'm sure somebody somewhere can talk about the fine line between the two, but yeah, it is the idea of chaos or disorder. And there's actually two laws of thermodynamics that deal with entropy. What the second law is, so there is, if you're having any trouble sleeping, one, you should go and meditate. But I used to joke that this chapter in the book would always be like 60 pages. Most of the chapters, usually chemists and physicists are very succinct in their wording, but this chapter is super long, and so you could read it if you're having any trouble sleeping. But the idea is that the entropy of the universe is always increasing, so it's greater than zero, and so we're expanding, right? Our universe is expanding. So that's one belief, and that's the belief our math system goes on. But there is something important here, and that is that there is always a system and the surroundings. In chemistry, the system is what? Well, what is chemistry?
The reaction?
It is. It's a study of chemical reactions. So the system is the reaction, and the surroundings is you and me, everything around it. So our body is a whole bunch of chemical reactions going on, and then it's, right, we get warmer or colder. So the system is the chemical reaction. When you do this in physics, the system will be something a little bit different than that. But then the surroundings would be, if we were in lab, the test tube, the flask, the burette, whatever else we have going on. All right, entropy is a measurement of disorder. So there is no such thing as order. There is only disorder. Keep that in mind. And so you can have an increase of disorder or a decrease. You could have more or less disorder. You can actually have S, whereas like heat is always changing heat. So entropy, I don't know how they can do this. They can actually measure the entropy, or say they measure it. But we're going to be doing chemical reactions. So we're going to be looking at changes. So the delta S, and you got to go back. Well, we'll come back to it in a moment. So for a positive delta S, that means an increase in disorder. So disorder is increasing. That is a positive thing. Keep that in mind. You guys go home, if you go out, you come home, you get done with your test, what did you do? Did you go and clean your house? Maybe somebody did. But the natural state of stuff is you just want to, like, the class gets over, let's do it after the next one. You just want to, like, it takes effort to put everything away nicely into a nice file and put it away. You just kind of want to throw it all up, the 52 card pickup. So with that, negative is a decrease in disorder, so less disorder, and that is a negative value. Your teacher sometimes, because I haven't gone through and found everywhere I wrote that, sometimes I call that more order. But again, that technically there is no such thing as order. There is only disorder. There's either more or less of it. So you can kind of ponder that. And so with that, positive is considered favorable. Because you're going to hear me say this, that it's favorable for entropy, but unfavorable for enthalpy. So an increase in disorder is going to be a happy face. There are going to be some of you who are going to dig my happy faces and sad faces as I explain it, because that's how simple my mind is. And there's going to be some of you who are like, I really don't like your happy and sad faces. And, you know, that's your problem. You don't have to use them. You don't have to write it down. It's your notes. I don't have to see it. All right. So before I forget, unless you're not saying it out loud, this is for all the people. Well, actually, somebody knows it. They could say it out loud. But if nobody knows it, does anybody know what the third law of thermodynamics is? You can email it to me in your own words. I find it fascinating what the third law is. I have to read the websites that are laws of thermodynamics for dummies. All right, we have to go back to exo and endothermic, which is enthalpy. Which one is the negative delta H?
Exothermic.
Exothermic. An endothermic is a positive delta H. So it's like your bank account. You're losing heat, it's negative. You're gaining heat, it's positive. This is the part that's interesting. Exothermic is favorable because losing heat increases the entropy of the universe. You can ponder that, or you can go and read the 30 pages that goes through that. And so endothermic, it's not that, well, we'll just say it's an unfavorable. It happens, and photosynthesis would be an example of an endothermic moving towards less disorder. But yeah, photosynthesis does happen. All right. I don't know who said that. That wasn't Damon, because now I can see him.
Oh, that was fun.
Oh, there we go. Your microphone does distorted stuff with you some days. All right, some generalizations about entropy. I'm trying to see if I'm missing anything. No. And this again is looking at it from a chemist point of view. Oh, if you decide to send me what the third law is, to get the bonus point, you can tell me why I'm dressed up like a butterfly.
So I just looked it up, and is it the entropy of a perfect crystal is 0 when temperature is 0?
0 Kelvin. Yeah. So when you get to 0 Kelvin, there's no movement. It is a theoretical point, and so it's the idea that they actually, a lot of places will say the entropy approaches a constant or something like that. But so, sorry, I lose track if I don't write it down. So, American way. All right. As a chemist, in chemistry, when we're looking at entropy, these are generalizations about entropy. We're looking at it for chemical reactions. And 99% of the time, we're going to be looking at it as state of matter. Damon answered it pretty much already. So the word chaos, the word gas actually is the word chaos. And so going from a solid to a liquid to a gas, that is definitely an increase in disorder or positive entropy change. So we're going to write some chemical equations or look at equations that are already written, and we'll be looking the state of matter. Like here, we're going from gases and we end up with a liquid. So we would predict, since we're ending up with a liquid from gases, this would be a decrease in disorder or a negative delta S. And we'll talk about enthalpy. Enthalpy is a little bit harder to predict. The thing that's interesting about predictions, today we're going to do math. I think on your study set for tomorrow, which shows up in like 2 minutes, but there's like one page is about predictions and just theoretical, and then one page is the mathematical stuff. All right, the thing is predictions don't always match the math, which is very interesting. So math, we all love the part when I get to the math because it's very linear and we get to a number. And some of you really like the linearity. That's why the titrations, the mice curves, it was very linear. But that's not actually how the universe behaves. If you think about it, watch your animals. They don't walk in straight lines. They walk in curves. Ponder that. Yeah. Or, right, if you drop a rock in the water, you don't see straight lines. You see arcs, right, or circles and stuff. All right, aqueous is the one that's fascinating. So this is usually going to be something like a precipitate, right? A solid to aqueous. I would think aqueous, because it's ions meandering, that it would make something have a pretty high disorder, like maybe more than a liquid. So the term liquid means you have a pure substance. Solid, liquid, gas is implying you have a pure substance. And here, a liquid is flowing. right? So it has more movement, and a gas is just chaos. So a gas is disorder. Aqueous means you have ions in the water meandering, flowing around. So that would imply more than a liquid. That's again a prediction. And however it is that they make the big chart that we're going to talk about is not always what we see. All right, complexity of structure. And this is looking at something, say, like CH4 versus C3H8. So anybody want to guess which one should have the higher disorder? And why?
Is it the first one?
No. Anybody else want to take a stab at it? And why?
The second one, because there's too many hydrogens.
There's more complexity. There's more bonds. The more bonds you have, the more complexity, the more vibes you're going to have. And so it kind of goes back to what Major had, he's like my champion Googler here, is when I asked what's the third law, is that perfect crystal, right? The perfect crystal has zero entropy. At 0 Kelvin is apparently a zero entropy state, which is interesting to ponder. It's a theoretic idea, but there's no vibrations, which means there's no vibes. Entropy is about, right, disorder. And so as you have more bonds, you're going to have more disorder. Another thing, which actually gets into the ionic solid, is, we'll just do an example here. So almost, again, 99% of the time, you're going to just be looking at states of matter. If there's a change in the state of matter, that actually makes a big difference. The difference between a solid and a gas is day and night in terms of disorder. The difference here is not huge. I used to have my numbers written down, but I don't on this. But for an ionic solid, just as you might see like a question that says, pick which one. So sodium chloride versus magnesium oxide. So something always has a higher entropy. So which one is it this time? Here, but this one's higher. And these, again, are generalizations for entropy. Enthalpy is something very different. That has to do with the nature of the storage of the energy in the bonds.
Is it magnesium oxide because it's bigger?
It is not.
It's not.
It is the sodium chloride this time. Any idea why? What's different about these? If you look at your periodic table, sodium's got a +1. Chloride's -1, so these are plus and a minus. And magnesium's next door, it's at a +2, and oxygen's a -2. So complexity of structure, like there's this whole hierarchy, but this is a weaker attraction. This gets into Coulomb's law, and again, when you take physics, that's like one of the first weeks in physics. But a weaker attraction, in terms of this, is disorder. So if they're not as attracted, you're going to have more vibes, more disorder. And so a weaker attraction means a higher entropy. Does that make sense? So we're measuring disorder or chaos. Again, the definition is always given as disorder, but you can think of it as chaos if that helps you, of giggles and jiggles and wiggles. So that's, I can't believe nobody brought, so the disorder is more giggles. When you're really giggling and jiggling and wiggling, you have a lot of entropy, and that is a good thing. That's really favorable. Ponder that. All right. So we're going to do these examples if there's no questions. Bought new pens. Somebody bought me new pens. So we're going to predict the sign. And so normally here I have equations written and we do it, except what I found one of the hardest things students have is I often have you, and we're going to be doing more of these tomorrow, is writing the equations from scratch. It is chemistry, and so this is your chance to shine and show what you know. So if we were in a normal 10 weeks, this would be like week 7, and this is where everybody's just like, oh my God, I'm not going to make it because there's still a month to go. But the good news is we only got like 10 days to go. You can all do it. We only got a week. So yeah, and it's going to be fun. Evaporation of water. So hopefully you all know the chemical formula of water. There's 2 H's and an O. And what's the state of matter of water? If it's called water, it is implying that it's a liquid. And it's evaporating. You can be on the board if anybody wants to tell me what we're going to end up with.
With 2 H's and 1 O.
No, we're just evaporating it. You're just going to end up with H2O as a gas.
Okay.
So, by the way, for all of you, this is not enough of a demo, but you can add more to it. So, changes in state of matter. You guys remember all your words for changes from a solid to a liquid to a gas? This is going from a liquid to a gas. So my question is our delta, we'll do it in blue, is our delta S positive or negative? And why? Going from a liquid to a gas, it's positive.
Positive.
More disorder.
All you're doing, there's more disorder. It's going to a gas. Gases are disorder. If you get with more gases, it's more disorder. Now on this one, we can actually also do our delta H. To evaporate water, you got to heat it. You're adding heat. So this one is also positive. So there are some, and usually the ones that I want you to do predictions on, you can make that prediction. We get only one happy face and one sad face on this. Just if you like the faces. All right. The pluses have nothing to do with the happy and sad. This means that we're increasing disorder. This means it's endothermic. Disorder, exothermic are the things that drive reactions. So we're gonna put it all together when we get to the bottom page. All right, we're gonna form iron trioxide. So forming means it's the product. Just so when you see it as words. So what's the 3 mean?
The charge of
It's yeah, we have iron's a +3 and oxygen. And you look at your handy dandy periodic table and oxygen, hopefully that's something, at least those of you who had me, hopefully you guys at least know oxygen's a negative too. So by the way, some of you asked about the peroxide experiment, or a lot of experiments have demos have peroxide. Peroxide's a -1. We'll talk about it when we get to oxidation reduction. And so when oxygen's not at a -2, it's not happy. All right, and we're making it from its elements. So we're just starting with iron plus oxygen. Diatomics. So everything we're doing with thermodynamics and into oxidation reduction, we can run into the diatomics. We have not seen them yet because we were dealing only with aqueous solutions. There's nothing about aqueous in this question. There's no water present. So iron trioxide, ionic compounds are going to be a solid unless they're dissolved in the water, but there's no water. It doesn't say, hey, we have ions here. Iron as an element is a solid, and oxygen, of course, is a gas. All right, what else is wrong with my equation, though?
Not balanced.
Balance.
It's, yeah, you guys remember that from way back in 221 and balancing, or 151? Some of you have been with me. I was thinking about that yesterday, like the whole year. All right, you can use whole numbers, in which case you'll get a 4, 3, and a 2. We're doing thermodynamics. This is where you're allowed to use fractions. So I'm going to use fractions because I'm allowed to. And if you don't like the fractions, well, there's sometimes it's kind of tough luck because we're in thermodynamics. But we're going to keep this as a 1, which means I need 2 irons and 3/2 or 1.5 of an oxygen. So 3/2 times 2 would give me the 3. And you should have learned that when you did your thermodynamics, that we suddenly balance with fractions. States of matter are key because now we're going to predict our delta S. And we can also do the delta H because I said here it releases heat. So releasing heat means it's exo or it has a negative sign. So if I ask, what's the sign for the enthalpy change, you would say it's negative, or I ask, is it exo or endo? You should be able to do it both ways. All right, so for the entropy change, again, S is entropy. Thank goodness it's not a verbal test, so you don't have to get all these words mixed up, because we have enthalpy, entropy, and energy. So delta S. More or less disorder?
Less?
Yes. Why?
Because we're taking the O from gas, which is the most disorder, down to a solid.
So this would be a negative because it's less disorder. We're going from a gas to a solid. So again, solid, liquid, gas, that's what they want to move towards. They're moving towards chaos. So trying to organize it, forming these crystals is always going towards a decrease in disorder. All right. If you like the faces, a decrease in disorder, oh, wait a minute, but exo, so we have a happiness hat. That's going to become important in a moment. All right, combustion. Anybody?
C3H8 plus O2.
Oh yeah, so propane, I don't expect that you know propane, but you guys can always Google it. But propane is C3H8. And we're going to do it as a gas. Combustion means, keep going, Damon.
It's combined with oxygen and left with CO2 and H2O.
Combust means to burn. All right. And yeah, this is the whole thing that drives our economy, drives our car, drives our bodies. The oxygen and carbon combine to form CO2. The hydrogens and oxygen combine to form H2O. So on a perfect day. When it's not so perfect in our engines, we get carbon monoxide and that kills us. So we have catalytic converters. And in our body, it's the water that messes up and makes these wonderful free radicals. Did we talk about them? H2O2, hydroxyl. That's so much fun. All right. So when you're writing combustion reactions, H2O you have a choice on. You can make it a gas or a liquid. I had a student who's a mechanic for race cars, he races, and he said combustions are always, everything has to be a gas. I'm a biochemist, so I'm looking in my body, and so I'm like, the H2O is a liquid. But if you want to do it simple and keep them all as a gas, we can do that. All right, to balance, we have 3 carbons, so we're going to need a 3 in front of the CO2. We have 8 hydrogens, so we'll need a 4 in front of the H2O. So, what's the number that goes in front of the oxygen?
2.
5.
It is 5. So 5 times 2 will give us 10. This will give us 3 times 2, which is 6, plus 4 from the waters. Each water has 1. So we have 10 oxygens on each side. We need to have it balanced to be able to do the delta S. Delta H. Combustion is what drives your car. Combustion is what warms your home. Combustion is what warms your body because it is, so combustion is exothermic. That you need to know because you're going to be writing combustions. I'll give you what this piece is. I didn't realize I left out propane. Oh, I knew it was notes and I could verbally talk about it. So delta S for our equation, because we're all doing it together, everything's a gas. And so if all your states of matter stay the same as gas, we actually count how much gas. Remember doing this with pressure way back with Le Chatelier's like 2-3 weeks ago? So on this side, and you only do this if there's no solid or liquid, we have 6 moles of gas. And on my product side, I have 7 moles of gas. Think of gases like 3-year-olds. 7 3-year-olds, you have a lot more chaos happening in your house. Or you can do puppies. 7 puppies. Araceli just got 2 puppies. Imagine 7 puppies. Got a lot more chaos than with 6. So chaos or disorder. So this is going to be positive. Disorder is a positive thing. We're increasing disorder. There are times where I'll ask it with words, and there's times when I'll ask for the sign. This one's an interesting situation because these are both favorable conditions. Now, Dr. Gibbs he gets to be on a stamp every couple of years in this country because he's considered actually one of the most famous American scientists. None of you picked him as your famous scientist, famous chemist, which may have been a good thing. His writing, his equation, we're going to dumb it down to our level or to my level. The background behind it, most people can't understand. It's quite esoteric to get there, but there was 20 years ago, a guy came out with a book of the 10 most important mathematical formulas ever that changed humanity. And this is one of the 10. And so you're going to be using this. In case, oops, sorry, that's delta H minus T delta S. I should have asked if anybody knew it. So delta G equals delta H minus T delta S. He called it free energy. They call it Gibbs free energy in honor of him. So like Hess's law, he didn't call it after himself. These guys all, Avogadro's number, it was named for him in honor of the work he had done. Because you guys weren't at the presentation, Mackenzie talked about it. Avogadro didn't come up with his number. So free energy doesn't mean the energy's free, although we do have sources on this planet, once we tap into them, that would be free. It is, in one word, does anybody know the one word that describes what free energy is? I'll ask this tomorrow and hopefully somebody will respond. It means spontaneous. That clarified everything for you, right? So in one word, like disorder, I write the word disorder and you're like, okay, I get the idea. It's like my room's a mess. You guys can't see what I can see in front of me, but my room is entropy. There's actually, none of you can get in to see my office. Usually at this point in the term, somebody will have a question. I don't know if Major ever saw my office, but he's laughing. My office has a note on the door that says, positive entropy in process here. Dr. Russell, on the other hand, his office is an example of negative entropy. He and I are like really close friends, and it's hard to believe because his office is as clean as can be, and mine is just like, I know exactly where everything is. All right, so spontaneous. I also don't have to count all the ones when I put like 8 ones for you guys. There's probably a connection there. Spontaneous, what it means, the best example of spontaneous, well, for chemists, in terms of what we've done, spontaneous means product favored. That is a definition that only works for chemistry. In physics, you'll use slightly different, but it means it's product favored. It means with everything we've been doing that we're moving forward. We're going forward. Without, this is the key part with this, without external influence. An example of, so spontaneous is negative delta G. So this is unfortunate. It drives most students crazy. A negative delta G means spontaneous. It's just how the numbers worked out. If you have a negative delta G, it's a go, where it's moving forward. So positive delta G, I don't have enough room. I pondered this yesterday. Positive delta G means non-spontaneous, which means we're going in the reverse direction. Or, so it either means we're moving reverse, or there is an or a but, or you must keep pushing. To make it go the way you want it to go. An example of spontaneous versus non-spontaneous is a battery, which is what we end with next in 2 days with oxidation reduction. So batteries are spontaneous chemical reactions. They're generating electrons moving in a spontaneous manner. What happens to your cell phone if you keep talking and doing all your data stuff? The battery gets drained and your cell phone's dead. And what do? Plug it in the wall. And the electricity in the wall pushes the electrons back. And as long as it's plugged into the wall, it's going to push, and it's going to, like right, a lot of you guys are on laptops, and I've done that when I go outside on my laptop, and suddenly it will say, hey, your battery's almost dead, and you just go and plug it in, and as long as those electrons from the wall are there to push it, our bodies are actually overall a spontaneous reaction because respiration is spontaneous. Non-spontaneous, photosynthesis. So what the trees are doing outside is non-spontaneous. But photosynthesis happens. What is pushing photosynthesis? It's not out there today, but it is, which is the sunlight. As long as you have sunlight, you all did this experiment in like kindergarten or first grade where you had the beans and you planted them, and some of them, those poor bean seeds, had to go under the cabinet and they never got any light and they never grew. They didn't die, they're dormant. They've had lotus seeds sit dormant for like over 1,000 years. It's kind of what some of us are. In some days, we're sitting dormant, waiting to bloom. So non-spontaneous does not mean it won't happen. It just means you have to keep pushing. So like if you're trying to push a snowball, a rock up a hill, you stop pushing, the rock's going to fall over you. There's always another way too. All right. In terms of what we're doing to get the whole big picture, product favored means K is greater than 1. Now, I want to point this out because we're going to get to K today. We're going to get to the math, which is wonderful because then we get a linearity there. You get numbers and you say, hey, it makes sense. When we're talking about delta H's, delta S's, delta G's, we're talking about positive or negative. We are comparing to 0. You can have positive numbers, you can have negative numbers. When we dealt with K, all the numbers were positive. It was the exponent that could be greater than or less than 1, because K is a ratio, and that's going to be different for these, which we'll get to in a moment. So in terms of my happy and sad faces in this equation, and we're going to work with that on the next page because I just not give myself enough room. This reaction that we wrote here for the combustion, if you have 2 happy faces, meaning it is exo in disorder, in terms of spontaneity, it means it will always be negative delta G. It's always spontaneous. So that's why I do the happy faces. Some people it really works for. If you have exo and disorder, both favorable conditions, it's going to happen. Don't have to worry about it. Now, I have to make a quick comment here. This is actually in the notes for tomorrow. Radioactive decay is spontaneous. It's going to happen. Uranium, it's going to decay. It can go through its 14 steps until it gets to lead. It's going to take 4.5 billion years. but it's going to happen. There is nothing about spontaneous and how fast. So we're all going to get through this. So actually, an example I gave is if Pimba was here, he could get you all up Mount Hood. He'd have to keep pushing and pulling. He's got me up there. He just keeps pulling. If you're attached to a rope and the Sherpa keeps pulling, you get pulled up there somehow or other. And then you're all going to come down. It might not be pretty how you all come down from top of Mount Hood, but you're all going to come down. You might not come down in one piece. It might be like a decomposition reaction. And it might take some of us a lot longer than others. I'm actually really fast going downhill. He's actually really amazed at how proficient I am at downhills. All right, so what we have here, a non-spontaneous photosynthesis would be both our unhappy faces. So it's basically the opposite of this reaction. So you're moving towards order and endothermic. And so it's non-spontaneous no matter what. You have to keep pushing. So again, non-spontaneous doesn't mean it doesn't happen. It just means you have to keep pushing. The sun has to be out. Photosynthesis doesn't happen at night. All right. So have you ever seen, this is more for Damon, there are these snails or slugs, and they're on somewhere in some island somewhere that go through photosynthesis. There's actually animals that go through, and so they have like their back opens up, and it's like this it's like a photovoltaic panel opens up, and they do photosynthesis. It's really pretty amazing what has happened with some species. All right. If you have one favorable and one unfavorable, these two are temperature dependent. And when we go through this on the next pages, there's more room and we'll see that these are temperature dependent. And there's a really quick and easy way to get this. So it is if you have one happy and one sad, temperature determines how to make it a negative delta G. If they are both positive signs, or if it's endothermic, it likes high temperature. Should have done that in a different color. And everybody's Wi-Fi's are going funky. And then number 2 is an example of low temperature. So normally I have the board to write all over. I should have scratched a piece of paper. So this situation is spontaneous if we keep the temperature low. This one is going to be spontaneous if we can keep the temperature high. And we have examples of that on the next page. So this is kind of like the big overview. And as we get through the next 2 days, and we'll do more examples with this tomorrow, but this is what we're leading to. These are the 3 terms we'll talk about. Again, delta H is a measurement of heat. So that's exo-endo. We've been dealing with that. Entropy, and that one's easiest to think about because you actually feel warmer or feel cooler. So if you're losing heat, the system is losing heat, we would feel the warmth. Entropy is disorder, and free energy is that the reaction is a go in the forward direction. All right. So we're going to do some calculations now. And there is a huge chart. I made mini charts so that I could do this without the big chart. You do not need to print the big chart, but you may. And so I'm sitting over somewhere else. The big chart is going to have a list. You guys should have seen this back in 221, whoever you had as your teacher. There's 3 columns in the chart. And back in 221, we only looked at delta H, and your teacher probably said, don't worry about the other ones, you'll get to it. And this is where we get to them. So you have a column that's enthalpy, a column that's entropy, and a column that's free energy values. And what we're going to do, does anybody remember the equation? We're going to calculate delta H of the reaction, then delta S and delta G using the chart. This is where you do the sum of the delta H's of the products. This is the official way to write the formula. That's the sigma sum minus the sum of the delta H's. It's the same equation for S of the reactants. That's the full way to write it. Or if you prefer, you can write products minus reactants. Final minus initial. So I want to point this out. We've been doing equilibrium expressions. We're going to, on the next page, put this together and change our delta G's to equilibrium. Equilibrium was a ratio of products over reactants. This is now adding and subtracting. So we're going to walk through the delta H together. And then to do the delta G, you can use this chart, or we're going to do it with the equation delta H minus T delta S. Unless you're given a temperature, which might happen tomorrow or on Thursday, standard temperature is no longer 0. The 0 degree standard temperature is only true for gas laws. I have no idea why they made that. It is 25 Celsius, which is a pretty useless number because this is all going to be in Kelvin. Because of the question I asked that Major answered, that the third law of thermodynamics, so entropy, because it's movement, chaos, giggles and jiggles and wiggles, we want to look at Kelvin because Kelvin was the only temperature scale that considered giggles and jiggles and wiggles. So this is 298 Kelvin. You're going to always be using that number unless you're told otherwise. That is a really warm standard temperature. They've actually modified it. So if you decide to go into higher level chemistry and physics, you do whatever your lab is using a standard temperature. So most places are, I think, like 20 or 21 is some places, but in introductory chemistry and physics, we still are using, and all the charts are made with 25 degrees. All right, so by the way, I want to compliment every single one of you in this class. You can rewatch this like in slow motion instead of the 1.5 time. I have been so impressed with how everybody's showing their work and showing units, and I can follow all of your work beautifully and keep it up. And when you take physics, I'm sure whoever your physics teacher will compliment you. And organic chem, although it's not numbers there. So we're doing products. You do have to factor in the stoichiometry. So those numbers are going to be important. So 3 moles of the CO2. And that is why this is kilojoules per mole. And that's our number for CO2. Now, when you look at the big chart, this is the other thing with the big chart when you go to do your study set. The big chart loves, like some of you will love, that gives 5, 6, 7 sig figs. If you want to go with that many, go for it. You'll notice I round everything to whole numbers because we're in the ballpark. Oh, you guys didn't get to do the lab, so yeah, the labs are always like, yeah, we're in the ballpark. All right, and then plus 4 moles of my H2O. So please don't just say 3 times negative 395 plus 4 times that. You've got to have it fully labeled. So my water is 286. By the way, the chart is very much has numbers for H2O as a solid, liquid, or gas. So when you're using the chart, make sure you get the right state of matter. And so the H2O is negative 286. And then kilojoules per mole. Be careful of the positive and negative. That's kind of the whole point. So those are your products. And then our reactant is our 1 mole of the C3H8. And that one is negative 104. So the oxygen, let's talk about this. Delta H's formation and delta G of formation. The F stands for formation of a compound. So elements are 0. Everything has an entropy. So notice entropy is an S, it's not an SF. So when you look at the chart, you can ignore things like down here, aluminum, we can ignore, the hydrogen gas, we can ignore. Now, if it was hydrogen as a liquid or a solid, they have made metallic hydrogen, it would definitely have a number. Everything has a number for entropy. The other thing, so you would punch that in, and I'm pretty sure number is negative 2222. It's 4 twos. It is. We get a negative, that makes sense. It is exothermic. This is telling us it's exo. It is combustion. Combustion releases heat. That's why we use it. The heat heats the steam, and we move a turbine and we make electricity. Problem is, we're probably going about it all wrong. We want to move the turbine, but there's probably better ways to do it. All right. So you would do the same thing with the S. The only thing is you do have to include the oxygen. So you have to subtract both of these. So make sure it's all in brackets. So go ahead and set it up and solve for your delta G. And if you're, or you can take a 5-minute break. If you want, you can also try the next one. I'll put the answers up. I'm going to pause this. So we can do this one tomorrow. Maybe. So if you do the delta S, you're doing products minus reactants. We set it up all beautifully. And again, you've all been setting things up beautifully. Did anybody notice the unit is different? It is in joules. Entropies are actually really small numbers. So it's a measurement of disorder. The magnitude is 1,000 times different usually from our enthalpy and free energy numbers. So once you solve, you do want to change it to kilojoules. You can show the step, or you can just move your decimal, dividing by 1,000. So just the first time I'll show the step. Oh. All right, we'll do. So 1,000 joules to 1 kilojoule. The other thing is this unit is joules per Kelvin. Entropy unit is per Kelvin. The moles cancel out, so this one was just kilojoules, but this one will end up as joules or kilojoules per Kelvin. Kelvin is a capital K. Kilojoules is little k, capital J. You can ponder that. So it's negative. The negative is important. 0.333 kilojoules per Kelvin. That's important because when we plug in down here, we're going to have our delta H, which is our negative 222 kilojoules minus the 298 Kelvin, and then times negative 0.373. So the positives and negatives are the key. The good news is we don't have to deal with all those zeros. Remember at the titration, 0.000, whatever. But they do both need to be, and go to kilojoules. Delta G's are going to be really large numbers. And so our answer comes out around negative 2,000-ish kilojoules. All right, so that's with the math. Then you're going to be asked to explain. So our first piece, this is exo because we have a negative delta H. In this one, our second piece, we have a negative delta S when we calculated it, which means what?
Less disorder.
Decrease disorder. You're back. All right, so there's less disorder. And then here, we got a negative. This negative means it's spontaneous at 25 degrees Celsius or 298 K. So now we can do this question. at what temperatures is it spontaneous? I'm not just asking at 25, I'm asking all temperatures, what's possible. So you always have 4 choices. It's either an all, a never, ever, or it's either going to be high or low. Exo disorder is low temperature. We're going to actually do the math because there is a mathematical way to calculate what low temperatures. So there's a couple ways to do this. This was actually a trick a student showed me, and it does work. It does require that you're good with positives and negatives. But if both signs come out as a negative, it's low temperature, like negative temperatures. If both signs come out as a positive, then it's positive, high temperatures. If you get different signs, then it's an all or never. If it's an all or never, you're not going to do this math here. But I'm going to walk through and how this math works. It goes back to this formula. So this is kind of for Devin. He asks, prove it, prove it. The assumption that is made is that we say 0 is that teeter-totter. It is the cusp where something is spontaneous versus something is non-spontaneous. So we set it equal to 0, and we're going to solve for t. So we're going to rearrange. We're going to plug in. Now, if you set this equal to 0, because everybody teaches it this way now, we're solving for t. If you rearrange this, you do end up with delta H divided by delta S will equal your temperature. It works because you're saying we're setting it where it's spontaneous or not. So we would plug in. You have to have them both in the same unit. So the numbers we calculated up here are negative 22222. And our negative 0.373. So you can see these come out really large because the magnitude of the difference. There's always a but. So our temperature is 5,957-ish Kelvin. However, you have to tell me its temperature is below that. So when I say at what temperatures, first state low or high, all or none. If it's an all or none, you're not going to go through the math. If it's an all or none, you would get a negative temperature, and you can't have a negative Kelvin. But if the signs are the same, you can actually solve for the temperature. And then you don't want to put an equal sign. You would say temperature is below this. So basically, if we could get this hot, if we went to the sun and we got this hot, this reaction would stop. So if your spaceship was a propane combustion engine, you're like not going to work when you get to that temperature. All right. So it makes sense that it worked at room temperature because room temperature is below that temperature. All right, we'll look at this one tomorrow. Any questions? It's just the number crunching. Again, with your study set for Wednesday, you have study set, should have appeared. You're going to have a page that is just looking at stuff and saying this is exothermic or endothermic, and then you're going to have a page with the math. So that's solving using the numbers. That's finding the temperatures. We're going to solve for K. So we're going to do the top half of this page, and then tomorrow we'll look at non-standard. This is the equation that we use. And for Paul, we get to use this R. So the reason we're using this R is because it's in kilojoules. And delta G is in kilojoules. I do want to point out, because half of you had a different teacher, a lot of people teach it as 8.314 joules per mole Kelvin, and then you're going to have to change it to kilojoules. I just keep it as kilojoules, so I've already made the dividing. So I do is 8.314 e to the negative 3 kilojoules per mole Kelvin. So again, kilo is little k, Kelvin is capital K. All right. Wow, I gave us a lot of room to do this. So if it asks us to calculate K, it gave us the delta G is, you just state the formula. Oh, here we go. Somebody else. Somebody know what that little knot means, that little degree sign? After a lot of my stuff, you're going to see it happen. This actually becomes important tomorrow. Because down here, there's 2 delta G's. So there has to be a difference. This means chart value, which means standard. This is, somebody made a big chart and said, this is it. This is what it is. So it's considered the standard. And so that's going to be when we see the little knot. It's called a knot, K-N-O-T, but most people think of it as a degree sign. All right. I want to walk through the rearranging. You don't have to show this, but I'm going to show it this first time and then maybe never again. Where you're trying to solve for K. So to solve for K, you state the formula. You've all gotten that hang of it. We need to divide by the negative RT. Don't lose the negative. If you do, you'll know because your answer won't make sense. Oh, I have a natural log. We're dealing with natural logs again. Remember those? I got to get rid of it. Now, some of you have the solve button. I actually find the people with the solve button often get answers wrong because they have to type so much more in their calculator. The rest of you, how do you get rid of the natural log? If you look on your calculator above the natural E. Is that what you're going to say? Little e. This time it is little e. I don't remember who I had the conversation with 3 weeks ago. Little e and capital E are not the same thing. So e raised to the power of all of this will give us K. So e raised to the power, you can move the negative to the top, or we have negative 33.3 kilojoules. You can plug in and then rearrange. I just this time wanted to go through that. You have a negative. You can just state R. You don't need to write that number out every time. I'll know if you did it right because you'll have the answer right. And then this would be times, if I don't give you a temperature, it's 298. That you have to divide by all of that. And this is e to the power of all of that. So sometimes it can help to put it all in and then say e to the power of your answer. The negatives should cancel. And right, I got K equals 6.9 e to the 5th. So a comment about K's, you've heard me say this before. Maybe you didn't hear me, but I've said this before. K's can vary quite a bit. You should have noticed over the past 3 weeks that K's can be positive 10. Like last week, we did KSPs. You had negative 20, negative 30, negative 12, negative 5. So when you see my answers, like on the study set or on this page, look to make sure your exponent is the same as mine. If you got here 6.4 times 10 to the 5th, we're in the same ballpark. So it has to do with how much rounding. If you put it all in one step, we should be getting the same number. But especially on the study set, sometimes I may have rounded different, especially once we start using the periodic table and people round different with that. All right, you guys know this is really what the whole test should have been worth, is why does your answer make sense? Anybody wants to get up there? We got David, Max, Juan, Major, and Paul. Somebody else want to tell me why the answer makes sense? What does this answer tell us? 6.9 e to the 5th.
Bigger than 1?
K is greater than 1. What does K greater than 1 mean?
Product favored.
It's going forward. It's product favored. So why does this make sense? Anybody putting it all together? I know it's brand new. We just learned it a whole hour ago. It's like years in the stats pace.
Because the G is negative.
Delta G is negative. So if delta G is negative, that means spontaneous. Your K should come out greater than 1. This is the whole point of everything I've talked about. Well, not the whole point, but that's the big keying it all in. Why this week we suddenly go back and look at these topics we did before, because everything relates to equilibrium. All right. So we're going to skip some pages. We're going to come back tomorrow. And this page, we're going to the last page. We're going to do page 46. There's answers on there for Devin, in case you watch this. This is the old practice quiz, I think. So we used to have quizzes. For some of you, this would have been good because we just did everything in class and you didn't have to go home and like all you had was like a homework set. For some of you, that method wouldn't have worked as well, but we always did practice quizzes. So we're going to do this. We're going to do number 1 together. Then I'm going to pause and let you guys try. You're going to have to find the chart, or I can find the chart while you're looking too. I'm going to go through number 1 together. So number 1 and 2 is just we're just in our brains making predictions. I will give you either if the delta H is always written as an afterthought after the equation. So on this one, you just look at the sign. It tells you if it's positive, negative. On this one, I wrote it within the equations. Sometimes we'll actually give you a number, or I just wrote heat. So here, this is a product. So that is exothermic. Here, I wrote, if I actually write the symbol delta H, you're looking, it's positive. So that is endothermic. Does that make sense, the difference with those two? We might as well do 1 and 2 together because I'm on a roll here. All right. So this is what I mentioned. You will still see me say order and disorder. And so humor me, those of you who are very particular about me misusing the words. So it would be more disorder, which is a positive delta S. Or less disorder means Dr. Russell's office is less disorderly. He would have a heart attack there knowing that there's no such thing as organized. You can only have more or less disorder. You can never have everything perfect. There's no such thing. All right, so which is it for number 1? Why?
Because it's taking gases and turning it into a liquid and a gas.
State of matter. When you are looking at this, you're looking at state of matter. So Paul's got it. You're going from a gas to a liquid. So I didn't ask for the sign. Let's get rid of that there. Exo means we have a negative delta H. And order means we have a negative delta S. If they're both negative, what temperatures? We're not going to calculate a temperature. This is the all, low, high, never, ever.
Low.
It is low. So the other theoretical way to think about this is exothermic is favorable. So happy face means it's favorable. Order is disfavorable or unfavorable. I think I just used it right. So that becomes temperature dependent. This is exothermic. If we increase the heat, if we increase the temperature, it's going to go the wrong way. So we don't want high temperature. Exothermics like low temperature. That was the thing on the Mount Everest question. It was a low temperature. So low temperatures drive exothermic. All right, so the next one, we're looking at states of matter again for the order disorder. And since they're all gases, you have to count your gases. So you have 2 versus 3. This is only if they're all the state of matter is gas. So this is moving towards disorder because you're moving from 2 to 3 moles of gas. So one of 2 ways you can think about it. Endo is a sad phase, but disorder is a happy phase. This one's a high temperature. You guys really are just going to make cute little charts and then just always check it, which is really a shame that we don't think anymore. Yeah, I don't know what's going to happen when you guys move on and you have to start thinking. Or you could use it now. Or you can think endothermic is a positive delta H and disorder is a positive delta S. So if they're both positive, it's endo, or endo heat is on this side. And that makes sense. As we increase the temperature, it will drive it forward. The thing is, if you have something that is endo and order, you can keep cranking up the heat and it doesn't go unless you push it somehow. So the Le Chatelier's principle, there is a but to it. Your post-lab questions today, you always have to explain. Some of you have too much explanation, which is going to get you in trouble at some point, but make sure you answer the question completely but simply. It's really an elegant thing to learn how to give more simple explanations. All right, you guys need the chart. I'm going to pause this. You can find the chart so you know how to find it. I have to go find mine. All right. If you're working on it, keep going. If you're getting the numbers, I'm just going to remind you how to show your work. So you want to state your formula. You can just say products minus reactants, or you can write the official way. It's kind of a, depends if you like writing symbols or not. So it's products minus reactants. And you want to label, so your products are the water. You want to be careful because it's H2O, H2O2. I did, this is not quite the same chart. I posted for you guys because this was the chart. It used to be attached to the notes, but your teacher, apparently when you get an advanced degree, we don't know how to photocopy a chart correctly. But if you look at, yeah, maybe this is where hydrogen's not all there. That's why. But there's like H2O2, there's H2O gas, there's H2O liquid, and there'll be the three lines of it. And like I said, they all go to like, for the H2O 285.830, I just rounded them all to whole numbers, which is fine, or you can use lots of sig figs. All right. I'm going to use my numbers where I rounded, and you include units. So the moles will cancel. We can ignore the oxygen for the delta H, but not the S. And so minus 2 moles of the H2O2. So hydrogen peroxide. Again, the oxygen's oxidation number is what drives this. Actually, let me finish this, and then I want to go through something, because it does come up on the lab that you guys have today, and a couple of people have asked me this question. This is actually a demo I did. This is elephant's toothpaste, by the way. And for those of you who were with me back with 151 and 221, I did this demo in the pumpkin. So the elephant's toothpaste came out of the pumpkin. I don't know if you remember that. But hydrogen, we're going to do oxidation reduction numbers later this week. It's one of the big things from general chemistry. Hydrogen's always a +1. Does anybody remember when it's not?
When it's paired with a metal cation.
Oh, as a hydride. Yeah, it's a fair answer. Those of you who are in my class, we never talked about hydrides because nobody uses them. But it's really good. That's a great piece of information. It's when it's by itself as hydrogen gas, which does happen. Like if you've ever had a meals ready to eat, and then you can actually, you would never do this out in the field because you'd create a fire. Oxygen, though, has to balance. So the oxygen in water is the perfect oxidation number for oxygen, which is -2. But in peroxide, it's a -1. And it's miserable. It's extremely reactive because it's just wrong. And so it reacts to form a -2 and a 0. And so this was a question because it comes up in the lab, not with peroxide, but it's an example of an equation where one element both gains and loses electrons. So we'll be doing oxidation reduction later in the week. The question on the lab is to remind you, so in the lab, for those of you paying attention, the mercury does get oxidized and reduced. In that case, the mercury is at a +1 and it goes to a 0 and a +2. But when they're by themselves, they're 0 to oxidation reduction on Thursday. All right, we punch all that in and we get a number. -196. And it can be nice to write next to it. This is telling me it's exothermic. That's my delta H. Using different colors can be really nice for each one. So my S, similar idea, my 2 moles of H2O, which is 70. And again, these are in joules. So, and 1 mole of oxygen, you will have to look at, which is 205-ish. Good enough for me. Some of you it won't be. And then our 2 moles, H2O2. Just 110. And this comes out 125. I like to show my plus or minus. Part is teaching. Obviously, negatives you have to show. The positives you don't have to. When we do oxidation numbers, you do. Maybe that's where it came from. Positive means disorder, an increase in disorder. So moving towards disorder, and it's exothermic. This is actually important. Exothermic is favorable. Disorder, an increase in disorder is favorable. That is why here you don't solve. If you tried to solve, you would get a negative value. But anyway, this is going to be spontaneous at all temperatures. Temperature won't make an effect on this one. All right, to find delta G, we want to state our formula. Delta H minus T delta S. And you can also do it with the chart if you have the full chart, or yeah, that's an interesting, so it should come out the same both ways. That's a lot of work though. It's much easier to use Dr. Gibbs' formula. 298 Kelvin, unless you're given a different temperature. Which I don't know, we'll see that. And you want to change your joules to kilojoules. So just divide by 1,000. And we got number -234 kilojoules. Yeah. Which is product favored. If I ask you to explain, all you need to say, that's it. Delta G is negative. That means product favored. For calculating the temperatures, there's no need to, because it's exo and disorder. So exo and disorder is always. Woo-hoo. Again, they have different signs. We have a negative and a positive. The opposite of that, endo and order, is never ever. All right, but the equilibrium constant, we can calculate. So our formula, delta G equals negative RT natural log of K. You make a little page so you have a simple page of notes. You'd be like, no, I don't need to memorize anything. And then you rearrange, plug in, rearrange. So you can plug in first or you can rearrange first. That's up to you. This is our negative 234 kilojoules. R, just a reminder, is 8.314 e to negative 3, because we need to be in kilojoules. I wrote it out this time. When I did it on the previous page, I just left it as R. So you can just write capital R. You don't have to write the number out. Just make sure you use the right one. Temperature is 298. Then we have natural log of K, and you get this number. And then I'm going to ask you why it makes sense. Anybody? For the good of the order? K is greater than 1. Delta G is negative. Those both mean product favored. We're moving forward. That's how a chemist explains it. A physicist would say spontaneous, which to a chemist means product favored. It keeps going. Another example of spontaneous is Galileo's perfect hypothetical frictionless surface. And then he takes the ball that's made of the same material, and once you tap the ball, it goes, and it never stops moving. There's no slope, there's no friction, nothing's going to slow it down. But we got to go back to that first page and add that piece. I just realized I left that off. I was so concerned about so delta G is that it's product favored. You don't have to push it. There is a but. Like I said, there's always a but to everything. That's how they can keep it a law, is they keep adding to it. You must start it once started. So another example is the propane burning. That one was always spontaneous. However, you have to light the fire. Somebody has to ignite it, right? So you have to push that button that ignites the fire or strike the match. So you have to give it that first tap. And once you tap it, it goes on its own. The propane will keep burning until you turn it off. That's the idea. You and me, we're going to keep breathing. It's respiration is spontaneous. Keep breathing. It's good for you. But don't breathe like shallow and fast. And is there any questions? All right. Somebody tell me the study sets. So you have on for today, just lab 6, the QA. Have fun with your flow chart. And if you have late stuff, there's like a few people have a straight late thing. I haven't changed grades to 0 yet. So you have today's your grace day. And tomorrow we have a study set and a worksheet and then another one. So you should be able to work through it. I will stay after now. I will see you all. Goodbye.